So, yeah, just a couple of preliminaries. I've been co-author with Chris on exactly 2 papers, and one of them was Stationary is Dead, and like many others, exactly why I was afforded the honor, I'm not sure, but I certainly appreciated that. Certain amount of notoriety comes with being a co-author in that paper, and I tell people, you know, well, I fully concur with the message of the paper. I'm not sure I can find a single sentence in it that I wrote all of. The other was about a year later. I got an invitation for some reason from Nature Geosciences. I think it was one of the News and Views things, to write something about sea level change and land storage of water. Exactly why I was contacted, I don't know. But I had the good sense to contact Chris and act to be willing to co-author, since he actually knew something about the subject. And I made a first cut at a draft. I'm not sure Chris actually said this is a good start or not, but the version that came back was, let's say, much, much better and much rewritten. I want to sort of fast forward to 2016. Chris invited me out to GFDL to give a seminar, very nice visit. I can't remember exactly what seminar I gave, talked to a lot of people, and Chris took me out to dinner. And we got to talking, and I think his son had run, perhaps the summer before, run across Canada pushing a cart, and I mean like 4,000 miles across Canada. Somehow we got around to, you know, sort of wished, you know, what we'd done and hadn't done when we were younger. And the one thing I said is the previous summer I'd hiked a short section of the Pacific Crest Trail east of Seattle in the Cascades, and, you know, it would have been really nice when I was younger to do the whole thing from Mexico to Canada. Chris's comment, which I clearly remember, was, well, you could still do it. And, you know, after that, I got to thinking, and the next summer I did a little bit more of it. And then in 2017, I got serious, and I actually finished the Pacific Crest Trail summer before last, all 2,600 miles. And Chris certainly played a role, because I don't think I would have thought it was even possible without that comment. So flipping to the topic at hand here, I'm going to talk a little bit about Chris and Krista's 2020 science paper. I think I ran into Chris at a meeting somewhere when the paper was just about to be submitted, and he was good enough to send me a pre-publication copy. It happened to be in the winter of 2020 when I teach a graduate class, and I gave them the assignment of seeing if they could reproduce some of the results, but more importantly for me, try to extend them across more of the West. This is the paper, Colorado River Flow Dwindles. I would say you could also title the paper, It's the Evaporation Stupid, which is really driving those changes. And there's been a lot written on changes in Colorado River flows. It's a really important problem. But understanding just exactly why this paper really brings it into focus. So these are a few visuals out of here. The short version, temperatures, which is B, going up. Everybody agrees, everybody's analysis agrees on that. Pretty much everybody agrees the long-term snow water equivalent has been going down. Paper shows the albedo changes that go along with that. D, and net radiation, E. The interesting thing is that A, which is the precipitation, most analyses show, like that one, it's pretty flat. That what's going on is not related to precipitation. So what we were interested in looking at, characteristics and drivers of the sensitivities across the western U.S., and in particular at the Huck 8 river basin level, of which there's like 569 of them or something like that west of the Continental Divide. That was our domain. So what we, and I should point out here that the second author, Saux and Vaughn, on this talk is really the first author on a paper that at some point will come out and has done all the work on this. But it's simply based on a model experiment with 1 degree C warming, looking at the sensitivities of the runoff which is the variable that was in the original paper, and the net radiation sensitivities, and kind of trying to connect them. So there's the domain. That's all 569 in the Huck-2 river basins, of which there are 5 in total. And so sort of the results of the experiments, running the long-term simulations, looking at the change in the flow, the sensitivity in percent per degree C is over there on the left, and the DQ in millimeters is in right. And again, these are annual values. Okay, so the interesting thing is, and I don't know if my cursor shows up or not. Does my cursor show up?
Yes, I see it moving.
Okay, you can see it. So this is the Upper Colorado River Basin, which was the topic of the original paper. And you see a bunch of yellows, which are the large negative sensitivities. In fact, I think the paper for the Upper Colorado River Basin gets something like -9. Our numbers tend to be a bit lower, but this pattern in the Upper Colorado is there. There's also kind of a bullseye up here in Idaho somewhere, and then some high values around here. If you look at just the flow sensitivities, it's not very surprising. The Colorado River is just a little trickle. It's a very important trickle, but compared to the runoff in the rest of the West, it's a trickle. So the actual DQs in millimeters are pretty small. But the changes, it's a really big deal, okay, if you're a water user in the Colorado Basin. So this is just looking at the annual ET as well as the runoff changes, and then the net radiation changes in watts per square meter. These are on an annual basis, I believe, so they're small numbers, but over a short period in the spring, they're much larger. And the general pattern in the ET and the net radiation changes is roughly similar. So here's the big story, which was in the, what did I do there? Oh, in the original paper, springtime. I wish I could get this control panel. Whoops, now I didn't want to do that. Now I lost my, oh, okay. I've got this control panel over part of my visual here, but I'll deal with it. The spring number is the big number, and it turns out that that number, and this is in the original paper, is a relatively short window in the spring, when in the warmer climate the snow is gone at high elevations, and so you have a much lower albedo than you do when the snow is there, and that's what's really driving this. A little bit of change in the winter as well. So what we've been doing is trying to look at the Huck 8 basins where these changes are largest. And what we've seen is that if you take the runoff coefficients, and these are annual runoff coefficients, and rank them across these 569 or whatever basins, that there's a window between about 0.2 and 0.6 in the annual runoff coefficients where the correlation of the runoff sensitivity and the net radiation is highest. For smaller runoff coefficients and larger runoff coefficients, it's smaller. And we take that as an indication for the small runoff coefficients. These are mostly arid, semi-arid areas. And for the largest runoff coefficients, these tend to be more coastal locations where there isn't that much, they're more rain driven. Okay, so it's kind of that intermediate range where the changes are the biggest. If you look at that, the right plot is just the outline of the ones that are in red across the US. So the gap kind of in the southwest where there's nothing shown is going to be the small runoff coefficients. The ones up in the headwaters of the Columbia and along the Pacific Northwest coast are the ones that are very large. But most of the rest of it is showing a pretty substantial signature. And the plot on the right, which unfortunately I can only partly see, but is the stream flow sensitivity, just a scatter plot, the stream flow sensitivities versus the melt period net radiation change in percent per degree C. And that's got a pretty strong negative correlation. Those are plotted only for the basins with the runoff coefficient in that 0.2 to 0.6 range. Other thing we've looked at is the relationship of these stream flow sensitivities along the x-axis in percent per degree C with the baseline annual mean sweep. They tend to go up in absolute value or down in a specific value, with the largest box being minus 7.5. Snow coverage and cool season temperature, those all go in concert. Not surprisingly, this is all related to snow effects, which is clearly where the signature of the mechanism is greatest. So these are kind of tentative key points out of what we have so far. The ET-driven sensitivity is strongly related to the snow-enhanced net radiation, as was shown in the original paper. It pertains across much of the rest of the West. It's greatest in these basins with intermediate annual runoff coefficients, and it tends to be largest in the basins with lower winter temperature and higher snow cover. So it pretty much confirms that this mechanism in the Colorado, although it's somewhat modulated, exists across much of the West. It's probably most important in the Colorado because the annual stream flow changes there are absolutely critical, because the reservoirs are very large. So changes in the seasonal runoff generation don't make so much difference in the Colorado. In the rest of the West, they're more important. So the mechanism is probably most important in the Colorado, but it does exist in most of the rest of the snow-affected West. So I'll stop there. And how do I get, okay, Chris, you're there, I see you.
Yeah, hey, Dennis. It's good to be reminded that I somehow contributed to your making that trek along the Pacific Trail.
Well, it was actually a big part of it, because I wouldn't have thought of it. I mean, you know, I'd done 70 miles at the time we talked, and it's 2,600 and some, the whole thing. So I just did a little tiny part of it.
I will give some credit to Edmund, my son, also for doing it. As for it's the evaporation, stupid, you know, I put a lot of work into that title that I made. It tried to tell the whole story, but I kind of like yours, although I would tweak it to say it's the albedo, stupid.
Yeah.
Because,
yeah.
I mean, evaporation is just a different, obviously it was going somewhere. Now I just had one question, you know, minus 9% per degree versus minus 5 for the upper Colorado River Basin. Can you explain the discrepancy? Do you have different snow albedo kind of relations, or did you get to look at that? Because, you know,
we've sort of struggled with that, and we need to understand that better. So to go back a ways, when you first gave us a copy of the paper, and I decided this would be a great project for the students and suggested that they reproduce it, we've actually used that monthly water balance model, which you used in some other work. And so they started out with that. And, you know, they struggled a bit, and I think, frankly, we had tweaked the model a bit, and there's probably some adaptations of it that aren't quite similar. We couldn't get back to exactly the same numbers. And then we sort of said, you know, it's a long story, which I won't go into the details, but let's just take the BIC model, which we know, and go do the simulations there. Now, you know, as you're well aware, because I think the paper may even mention this, there's a wide range of these runoff sensitivities, right? And in fact, there's a paper that came out not too much different from yours a year or two earlier by Marty Hurling, based on GCM results and so on. And it gets numbers like -2 or something, I think.
Yeah, I'm well aware, yep.
Yeah. Previous results of ours, I think, from Julie Baino's work were maybe in more the -6. You may have a better memory than I do. We didn't get as high as -9, I don't think. But yeah, we need to understand better why that difference. Factor of 2 is a big deal.